Hello students, in this lecture today we shall learn propagation of errors and errors when we approximate any function. So these are the prerequisites for today's lecture. First is error and its types, next is significant digits, next is rounding of a number, and at last partial differentiation. So before knowing what is propagation of error and how it occurs, we should know about these topics. Our objectives of today's lecture are to understand the propagation of error while performing simple arithmetic operations like addition, subtraction, multiplication and division, and we shall find estimate of the error when we approximate any function, either it is a function of one variable or more than one variable. Now we are starting our today's topic. By propagation of errors, we mean an error occurring in the succeeding steps of a process due to the occurrence of an earlier error. For example, we are given suppose two numbers, and these numbers are rounded off to some significant digits. Then these numbers will contain some round off error, like we have 8.45 and another number 7.31. Now if we round off these numbers to one decimal place, it means 8.45 will be converted into 8.4 and 7.31 will be converted into 7.3. So when we add these two numbers or we subtract one from another, or we multiply or we divide, then the result will contain errors as we have rounded off the original numbers. Similarly, if we have a function of one or more independent variables, and suppose we made any mistake in calculating these variables, then dependent variable will also becomes erroneous. This is what we call propagation of errors. Suppose we have a cylinder and we want to find the volume of that cylinder. So we know the formula to find volume of a cylinder is pi r square h, and we write V is equals to pi r square h, where V stands for volume of the cylinder, pi is a fixed number, r the radius of the cylinder, and h height of the cylinder. So we say that V is depending on two variables r and h. Now suppose if we made any mistake in calculating the radius or height, then the value of the volume will be erroneous. Now in propagation of error, now we'll see the error in addition of n numbers. Consider the exact numbers x1, x2 and xn. These are the exact values of n numbers, and their approximate values respectively are x1, x2 and small xn. Let delta x1, delta x2 and delta xn be the errors in these approximate values x1, x2 and xn. Suppose we are given two numbers. One is 8.36 and the other is 2.64. Suppose we rounded off these two numbers to one decimal place, then 8.36 will be converted into 8.4 and 2.64 will be converted into 2.6. So 8.36 and 2.64, these are the exact numbers, and when we rounded off these numbers, we have got the approximate values, and these are 8.4 and 2.6. Now if we add these two numbers, then the result becomes erroneous. Now see here what we have written: xi is equals to xi plus minus delta xi. This plus minus delta xi, this delta xi is the error in the number xi, and why we have written here plus minus, because in general we don't know the sign of the error. It may be positive or negative both. As you can see, we have taken one number as 8.36, and when we have rounded off this number to one decimal place, we have got 8.4. So error is what? Error is the difference of approximate value and exact value. So when we subtract 8.36 from 8.4, we will get a positive value. Now the other number was 2.64. So 2.64, when it was rounded off to one decimal place, we have got 2.6. Now error is equal to approximate value minus true value, so this will give you a negative value. Therefore error may be positive or negative both. Therefore we have written here xi is equals to xi plus minus delta xi. I is equals to 1 to n. Now we want to add these numbers. Therefore if we add exact numbers, we will get the exact sum. So this is represented by capital X here. X is equals to x1 plus x2 up to xn, and small x is equals to, this is the sum of approximate values of these numbers, x1 plus x2 up to xn. So if we want to find the absolute error in sum of these numbers, therefore what we will do, we shall subtract small x from capital X, and we want to find absolute error, therefore we will apply the absolute value function here. So we are getting mod of x minus x, this is equals to mod of x1 minus small x1 plus x2 minus small x2 up to xn minus small xn. Now using the property of absolute value function, we shall get here capital X minus x. This will give you the error in small x. So this quantity will be less than or equal to mod of delta x1. This is the error in the first number small x1, then delta x2, and it is the mod of delta xn. Now see the estimate of error when we subtract one number from another. Again we are considering here two exact numbers, capital X1 and capital X2, and their approximate values respectively are small x1 and small x2. Again delta x1 and delta x2 be the errors in the approximate values x1 and x2. Therefore I have already told you that error may be positive and negative both. Therefore capital Xi will be equal to approximate value xi plus minus the error in that value delta xi. I is equals to 1 to 2. Now what we want to calculate? We want to calculate the error in subtraction. So first we have calculated the exact value, x is equals to x1 minus x2, and small x is equals to x1 minus small x2. So this is the approximate value of the subtraction. This is, and capital X1 minus x2, this is the exact value of the subtraction. Now we shall calculate the absolute error. So absolute error is given by mod of true value minus approximate value. So it becomes mod of capital X minus small x. This will give you mod of x1 minus small x1 minus capital X2 minus small x2. Using the property of absolute value function, we shall get here mod of delta x. Delta x, this is the error in x. Delta x, which is less than or equal to mod of delta x1 plus mod of delta x2. So what we have seen, if we add n numbers or we subtract two numbers, we consider subtraction of two numbers, then the estimate of absolute error will be less than or equal to sum of the individual errors in these approximate numbers. Okay, now see error in multiplication of two numbers. In our earlier slides, we have seen the error in addition and subtraction. Now we'll see the error in multiplication of two numbers. So let us consider two exact numbers, capital X1 and X2, and their approximate values are small x1 and small x2 again. Also, delta x1 and delta x2 be the errors in x1 and x2, the approximate values. So again, we can write capital X1 is equals to x1 plus minus delta x1. I've already told you that there is we cannot tell the sign of the error, therefore we have used plus minus sign here. So capital X1 is equals to small x1 plus minus the error delta x1, and capital X2 is equals to small x2 plus minus delta x2. Now we multiply the exact numbers. So x1 into x2, this will be equal to, when we multiply this quantity with this one, we'll get x1 x2 plus minus x1 into delta x2 plus minus x2 into delta x1 plus minus delta x1 into delta x2. Okay, now we shall calculate the absolute error when we multiply two numbers. So how can we calculate these? We can calculate the absolute error by subtracting the approximate value from the exact value, and after that we will take the mod. So mod of x1 x2 minus small x1 into x2, this quantity will be less than or equal to mod of x1 delta x2 plus mod of x2 into delta x1 plus delta x1 into delta x2. Since this quantity is very small, this is a very small quantity, delta x1, since it is an error, therefore it is a very small quantity, so we can discard it. Okay, so if you want to find the relative error in this product, then first of all you should recall what is relative error. Relative error is just when we divide the absolute error by the true value, mod of true value, then we will get the relative error. So relative error in this product will be equal to mod of x1 x2 minus a small x1 x2. This becomes absolute error, which is divided by mod of x1 x2. So you'll get here delta x2 divided by x2, its absolute value, plus delta x1 divided by x1, its absolute value. We have discarded this number. Okay. The error in division, I'm leaving this to you as an exercise. I'm giving you two exact numbers, x1 and x2, and their approximate values are small x1 and small x2. Delta x1 and delta x2, again these are the errors in the approximate value of these numbers, x1 and x2. So we can write capital X1 is equals to x1 plus minus delta x1 and x2 is equals to small x2 plus minus delta x2. You have to find absolute and relative error in the division of these two numbers. Now see one example. Estimate the absolute and relative error when we add root 6, root 7 and root 8 correct to 4 significant digits. So first of all, we shall find the true values of root 6, root 7 and root 8. So the true value of root 6 is 2.44948 and so on. It is non-terminating. Root 7 we shall get 2.64575. Root 8 is equals to 2.82842. Again it is non-terminating. Now we shall round off these numbers to 4 significant digits. Therefore we'll get approximate values of these numbers. Approximate value of root 6, this is equals to 2.449 when we round off this number to 4 significant digit. Root 6 2.449, root 7 2.646, root 8 it is 2.828. Now we shall find the exact value of the sum of these numbers. Capital X is equals to root 6 plus root 7 plus root 8 and small x is equals to 2.449 plus 2.646 plus 2.828. Now what is the estimate of absolute error? This will be less than or equal to mod of 2.44948 minus 2.449 plus this and plus mod of 2.82842 minus 2.828 means absolute error will be less than or equal to 0.00115. Now if we want to find the relative error in the sum, therefore what we shall do, we have to divide the absolute error by the true value. So mod of capital X minus small x, this will be divided by mod of capital X, and this quantity is also less than or equal to 0.00115, which will be divided by the sum of these three numbers root 6 plus root 7 plus root 8, and it is equals to 0.000145135. Now see error in the approximation of function. If f is a function of several variables capital X1, capital X2 up to capital Xn, then the estimate of maximum possible error in f will be mod of del f upon del x1. So what we are doing, you can see here that we have partially differentiate f with respect to all these variables, and partial derivative with respect to one variable is multiplied by the uh, error in that variable. So delta f, it is approximately equal to mod of del f upon del x1 into delta x1 plus mod of del f upon del x2 into delta x2 up to mod of del f upon del xn into delta xn. Now see this example. The strain in an axial member of a square cross section is given by epsilon is equals to f upon h square e, means epsilon is a function of three variables capital F, small h and e. The approximate values of these three variables are given by capital F is equals to 72 plus minus zero point 0.9, H is equals to 4 plus minus zero point 0.1 and E is equals to 70 plus minus 1.5. So these are the values of the errors in these three variables F, H and E, and 72, 4 and 70 are the true values of these variables. We have to calculate maximum possible error in the measured strain. So for solution, first of all we shall calculate the exact value. So epsilon is equals to 72 divided by 4 into 10 to the power minus 3 whole square into 17 to 10 to the power 9. When we calculate this one, we get 64.286. Now we shall calculate the error delta epsilon. This is equals to, since epsilon was a function of three variables f, h and e, therefore first we shall partially differentiate epsilon with respect to these three variables, and this quantity will be multiplied by the respective errors in these variables. Now when we put all the values here, just in the slide we have just calculated the partial derivatives, and we have put the values of errors and these variables. So here we get epsilon is equals to 64.286 plus minus 5.3955. So this is the estimate of error when we calculate the strain. And these are our references which I have used to prepare this lecture video. Thank you very much for your patience.